You've probably never actually seen one, right? But believe it or not, you are using billions, literally billions, of them at this very second. We're talking about the fundamental building block of all modern electronics, the bipolar junction transistor. It's a tiny, tiny device with an absolutely colossal impact. So let's dive in and see how this thing actually works. So how is all of this even possible? Well, it all boils down to solving one really fundamental puzzle. How do you control a massive, powerful river of electricity using just a tiny little trickle? The answer to that question is the secret behind every computer, every smartphone, and every satellite we've ever launched. You know, the easiest way to get our heads around this is with a really simple analogy. So for a second, let's forget about all the complex silicon stuff and just think of the transistor as the ultimate electrical valve. Okay, so picture a regular old water faucet. You give it a tiny twist with your wrist and boom, you can control this huge gush of water, right? A transistor does the exact same thing, just with electricity. A tiny little electrical signal at a control point precisely manages a much, much larger current. That's the core idea, the whole game right there. A small input controls a large output. All right, so that's the big idea. But how does this magical electric valve actually work on the inside? To see that, we've got to peek inside what's basically a 3-layer semiconductor sandwich. So what exactly is a BJT? Well, it's this 3-layer device that has two simple yet completely world-changing jobs. It can either amplify a really weak signal to make it stronger, or it can act as a perfect silent electronic switch. Amplifier or switch, those are its two superpowers. Each of these 3 layers has a very specific job. First up, you've got the emitter. Think of this as the source. It's heavily doped, which is just a fancy way of saying it's been juiced up with extra stuff to pack it full of charge carriers, all ready to flow. In the middle, you have the base. This is our control gate. And the key thing here is that it's incredibly thin and only lightly doped. And finally, you've got the collector, which, you guessed it, does exactly what its name says. It collects all those charge carriers at the end of their journey. Now, this semiconductor sandwich comes in 2 main flavors. The most common one is called NPN, where the electricity is carried by negatively charged electrons. The other is PNP, which kind of works in the opposite way. For our purposes, we're going to zero in on the NPN type, because it's the most common and it'll show us exactly how the magic happens. Okay, so let's get down to the nitty-gritty. How does this thing actually work? We're going to follow the journey of the electrons themselves to see how that tiny trickle of current really does control the river. Okay, step 1. It all kicks off when we send a tiny little positive voltage, our control signal, to that super thin middle layer, the base. Now that little bit of voltage does something really cool. It effectively lowers the barrier between the emitter and the base. It's like we just unlocked and opened the gate. The technical term is forward biasing, but all you really need to know is the gate is now open for business. And with that gate open, what happens? Whoosh! A massive flood of electrons that were all bunched up and waiting in that emitter are suddenly set free. The river is officially flowing. Now, all of these electrons surge across toward the base. And remember what we said is the most important physical feature of the base? It is extremely thin. And this right here is where the real trick happens. Because that base is so incredibly thin and so lightly doped, the vast majority of these electrons are just moving way too fast. They have too much momentum. They just fly right past it. They totally overshoot the mark. So what happens to all those electrons that just zoomed past the base? Well, on the other side, the collector is waiting. It's got a positive charge, so it acts like a magnet, pulling in and gathering up all those runaway electrons, completing the main circuit. And there you have it. That's the punchline. That tiny, tiny current we sent to the base just enabled a much, much larger current to flow all the way from the emitter to the collector. We did it. We control the river with just a trickle. Okay, so now we know how it controls the flow, but what can you actually do with that? Well, this awesome little trick lets the transistor perform 2 main jobs that changed the world. This control is measured by something called current gain, or beta. And the numbers here are just wild. For every 1 electron that goes into the base, you can get anywhere from 20 to 200 electrons to flow through the collector. That is an insane amount of amplification. So yeah, to put it simply, current gain is just that ratio. It's the big collector current divided by the tiny base current. It's basically the horsepower rating for the transistor's amplification power. And this incredible power gives it its two superpowers. If you operate it right in the sweet spot, in what's called the active region, it's a perfect amplifier, taking a small signal and making a bigger, identical copy. But if you push it to the absolute limits, either all the way off, which we call cutoff, or all the way on, which we call saturation, then it becomes something else entirely. It becomes a perfect silent digital switch. So what mode it's in all comes down to which of its internal gates are open. It's actually pretty simple. For an amplifier, that's the active mode, the first gate is on, but the second one is off. And to use it as a switch, even easier. Both gates off means the switch is off. Both gates on means the switch is on. That's it. So a tiny electrical valve that can amplify or switch. Okay, neat trick. But why is that the thing that built our entire modern world? Well, the answer is one word: scale. I mean, just look at this. An old school radio might have had a handful of these things. Your laptop CPU, it has billions. Billions. Your smartphone probably has even more. The growth has been absolutely explosive. We went from literally counting them on our fingers to packing billions into a space you can't even see. And that incredible density, that scale, is everything. It means the transistor isn't just another part. It is the absolute bedrock of our digital age. It's the beating heart of every single computer chip. It's the engine that runs all the ones and zeros that make up our digital lives. Seriously, from the phone in your pocket to the satellites flying over our heads, it all comes back to this one tiny, elegant little switch. Which brings us to a final, pretty mind-blowing thought. The very first transistor was about the size of a human hand. Today, we can cram billions of them onto the head of a pin. So as we get closer to putting 1 trillion of these things on a single chip, you just gotta ask yourself, what incredible problems, what impossible challenges are we going to solve next?